Hello boys and girls, nice to meet you again, and we are back with this new technique, for me at least. I was inspired like form structures, and this time I want to talk about how to simulate something more stable than just abstract splashy and swirly things in the water. Then we want to create some mask, something around here, and transfer this mask into the DOP content. Of course, I did want to render that as a form, with a white form with very nice bubbles, but it took me so long to render one frame. So I decided to do this like a soap, I don't know, more like in your imagination, I think. Then we will cover a few things, how to manipulate different states of a simulation, for example ages, how to separate, for example, some bubbles and kill it randomly, and that's it. Maybe a few words about render, we'll see how it goes, and I hope you'll find it enjoyable. Okay, we're inside our project. I'll go you through this project and hope by the end you will understand everything what I did here, with all the mistakes and all the insights I have. So first things first, I have this file with the geometry, match size to squish it into the square 1 by 1. You need to scale to fit and uniform scale to do that. Next was like to delete some boxes where I just selected it by manually. Transform that, split it, and have only these guys, the soap from here. So at the end of this chain, I just did different versions, and this thread is like giving the groups for every objects in the scene. And this way, if you do a group and do it with a primitive, you could use this group to shade your different materials, to apply your different materials for different objects in the one scene like this. So I just click add one here, for example, and have these different tabs with group selected, and I choose like material I have before prepared for this particular cases. So at the end, I decided not to do that because it was like too complicated and too long to do a render, even preview. So I just give it in one place. I choose like these two objects, and that's it. For the background, it was like grid. I bend it a bit, and that's it. That's our background. We could disable it, and I hope we could disable our soap as well, so we could concentrate what we have here. Also, I tried to do a volume. I just like use my simulation and convert. I think I converted in here somehow with particle, VDB to particle. It was there, but again, I just wanted to give a form a bit of a texture inside, and that was so long to render, so I decided to skip it in this example. So here is pretty simple. We have an object which we could use an object merge and link to our soap in here, right? Then I give it a flip source node. Flip source node prepare our geometry for the flip simulation. I use a particle separation to give enough resolution to have some particles here, and I use a primitive. It's a prim properties, this one, right? Prim properties. You could go to the volume tab, volumes, and check adjust visualization. And if you do with invisible of your volume, what you left with is particles, only particles you have. Then you go for the first simulation for spreading your like growing effect, and we do this with the group selection. We start with the in, it's just bounding sphere in here, which is select some points on our cloud points. Then we will use a pyrospread, so we need a temperature attribute in order to work with that. And I give it like a pretty simple expression when I check if in point group is equal 1. So I check the point group in, which is this one, and I say like if this is true, let's go a temperature of 1. What we have now, if we do with this icon, right click and go with the temperature, we have 0 temperature attribute for this guy, for all the points except this of this group. So this is a starting point, so this is like the source of our pyrospread. The next step, go to our pyrospread, and I think I need to do from scratch this guy just to show you what we can do to differentiate our spreading. So by default from box you have nothing. It's not enough search points, it's not enough radius for this guy to work properly. And what I usually do in this case is go to diffusion, and this is a representation of our noise. If we go here, you could see it's more smaller patches and smaller area. So go to the diffusion rate, this is the new one, and let's adjust it, make it much smaller. Let's change the offset. It's good practice to do to break things out. And as I could understand, this is like a higher volume, high temperature, and this is lower, like a cooler area. So from this point, if you go to visualization with temperature, check it again, not that much point, and you will control your spreading by these few parameters. The rate is like a speed. Let's start with 1 and adjust the search radius, like radius to the next point when we could burn it out. Give it much more neighbors point, and let me see if we get something. If we go with the, oh okay, we have something, but in this case we have higher cooling rate, which is like trying to cool your simulation down, your temperature. So if we're going lower, something like 0.4, we should see something, right? And this is your first spreading mask, and we will use this mask for different things in future in this project. So you could play around with these numbers. Rate is a speed, you could go much slower, but you need something to spread it initially. So, and then you could spread it much faster or slower. You could use your search radius, which is again give you a different look for this kind of stuff. You could go with 0.1, and this will give you different, right, different area. You have like much more differentiation for your noise. This is cool. This is quite easy, quite fast node. You could go in this fuel, maybe with contribution. This will affect your animation as well. And as a result, you have quite a few attributes to use. So if you go in here, you could use fuel, fuel grain, rest, temperature, burn. This is much more contrasty mask for you. You could use temperature, and you could check everything here, like even your noise could be multiplied, but not now. So I did this way. This is like a file cache, and again with the temperature, so we could see the spread. I have this pattern for this and null for a good measure to output from this chain. So the next step will be going inside your simulation. Okay, and I decided to do everything in Flip Solver because like I started initial with vellum grain and vellum fluid, and it's great for this small scale simulation. And even this this vellum grain, vellum fluid, for example, configure fluid, has great ability if you go allow editing of content, go inside, and somewhere in here, grain source, you could do uniform radius check oft and do different scale. But I think I had greater result to my eye with the flip fluid. It has this divergence field, which is great, and we'll use it a lot in here. And this will control our expansion of our point base of our mask, so it's great. And I couldn't find pretty much the same effect inside of vellum grain. I could use a vex or something when I search for some points and radius and try to pull that out from each other, but here it's much simpler. On the other hand, I couldn't, like, okay, if we checked here, I couldn't do like different p scale and consider that in our simulation. And if you have like some tips and tricks for that, it would be great to know, because there's like bubbles, and I want, for example, this big bubble to spread outside these bubbles around. And I, to be honest, couldn't figure out how to do that. And if you could, and if you know the method, please tell me, please write a comment and try to like figure out that together. Because I do some post-process for this guy, and that didn't work quite well for me. It gives me, I think I go with VDBs, and I try to figure out some volume sample and try to push particles outside of that, but that gives me like very glitchy effect, and that didn't work for me as well. So I tried to, as you could see, these bubbles just jumping around, and I tried to use a chop network, but that didn't work well as well. So if you have a method how to use your flip or DOP network and how to consider our p-scale inside the simulation itself, not just like visualization purpose, because this time we have these bubbles and they just growing during some time, and they didn't affect the bubbles outside of it. So that would be great. But let's back to our flip solver. It's a pretty standard solver. When you need a flip solver, you need a flip object, and you go from left to right inside of the DOP network and from top to down. So everything on the left will affect everything on the right. This is crucial when you use for your static object with a ground, for example, with the gravity. So you want your static object first and then the gravity next. And inside here, I started with the p-scale, with the random p-scale for your particles, right? And probably I want to do it this way, and I want to see what we have here. And one more thing, when we're here, you could lock this view and go inside your DOP network and see what we get like live. Inside of Flip Solver, we need to link your TOP, your source, which is a primitive we used before, which is this one, I guess. And you want to use the same Parquet operation as we had before. And you want to change your particles under the guidance tab. You want to change because you have spheres and you want to change particles. And that's it for it, I think, right? For now, let's go. Oh, and for this is very crucial for this example. Go back to your initial tab and add this velocity attribute, because by default, if you go invert the default, that is turned off. So you want add viscosity attribute, you want to add temperature attribute, and you want to add your divergence field, because without that our ferret didn't work, and I had like a headache trying to figure out what is wrong when we use your divergence field onto your particle flip solver motion volume, and you checked here and you have everything, but you see nothing because of that little guy, little mark that you need to check on. So be aware of that. And I think the same true for this guy. When you go to the flip solver, go to particle motion and go to behavior. Later on we will use your ID. In fact, use it here. So when you write something like that in the flip solver, you rely on your ID and you want this ID but by default this ID is checked off. So you will see nothing because in terms of variation of EP scale, because your ID is off. And now you see this EP scale is considered your ID. And again, one more thing is H particles. We will consider that inside of SOP solver, and you want to like calculate the moment the particle burns or the moment the particle changes something. You need this attribute as well. So the next thing would be our process of how to transfer this mask of temperature, because this is a mask for us, inside of DOP solver. Because by the default, if you try to use your temperature or mask or anything outside of DOP network, that will consider only the first frame. So you need to consider your mask every frame of your simulation or every substep. And you could do it by different ways, but I will use a SOP solver. And that will give you ability to manipulate the geometry from here. So before we go inside of a SOP solver, I want to go back and just mention that I use volume source for the last input and use it for the first frame only, and use a preset and link to the first content geometry. Content. This will give me some variation because we source it already from here on the flip object, but this will give me just a bit more for particles and just a bit more of a variation. So you could use this volume source with a constant source when, for example, if I do it this way and I disable this guy, that will give me like sourcing particles every frame. And if we were to add a gravity force, could you see something or not? No, this is wrong. This is switch because we used like file cache before. Once again, that will affect our geometry, right? And this is like usual case of your flip source simulation. So go back, disable it, delete volume source, and what else we have here? I think nothing. So we go through these attributes, go through these attributes, these three, because it's very important before we go inside of SOP solver. We go inside of SOP solver, use object merge to grab our particles from the SOP level, transfer that temperature attribute for this time for our particles inside of our flip DOP network, and then we do quite a few attribute triangle, and I separated it. So here temperature is a temperature. We give another attribute for the temp just for visualization, and I wanted to separate our temperature from the top temperature we had before. We have some viscosity at the initial state for our particles. It was like test. So and now we could give again pretty simple condition when we say if temperature is more than 0.5. Let's use our divergency. Divergency field. In order to use that properly, we need to go to the flip solver, go to volume motion, and go to this tab divergence. We need to turn that on. That will give us an attribute called divergency, and we could refer this attribute and manipulate it in somehow. So now we separated particles based on our temperature attribute. And this way we have zero divergency for this field, and we have some expansion because divergency field is like expansion over particles, and if you use a negative number, that will do opposite, I think, right? That will suck our particles inside of itself. Next thing I did was like a little bit of drag for the velocity. So if you multiply your drag over your velocity by some number in the dop content, that will apply decrease in your velocity over time. Then I gave a little bit of viscosity for these growing particles, because based on this condition, we apply all these attributes only for this only for this red part. The next thing I did was like you could use this i.grop expression underscore and give you anything you want. This is a name for your group and equal to 1. This will create a group with this name, again based on this condition. So every particle that goes in this condition will go into this group, which is called grow. And you could see this is this group out here. And this again was like a test before. We could delete this, and I gave a droplet of 0.2 for this group. And again, in order to do that properly, you need to go to the solver, and you want to go, I think, somewhere here and enable your detected droplets. It will separate. When we have enough separation, Houdini will decide how to conform your droplets out of your flip simulation. We need to play with numbers. I just open the documents and try to figure out something, but I'm not sure if it has any effect at all for this. Okay, what we have? We have some attributes. We have one group based on this temperature. Then we want to go further and use this group. So now we are working on this group, which is our again red particles, and we want to add something more. In this case, we want to separate another group, and we want to use this group at the bigger particles, so this bigger bubble. So give it a name. Group name is grow, which is this one, right? Go inside and say something like random number from ID, which is 0 to 1 number for every particle, is more than some threshold, some channel number, and yeah, I used this number. If this is true, let's go and create another group called bubbles equal to 1. Let's go and give this group some attribute called action and give it 1, and change some temperature for this bubble. Now when we do this, we go another if and set something like we check the attribute action, and we say something like if the action is equal 1, we check if that is true. Let's go to the attribute, new attribute, and call it new h and say plus plus, which means pretty much the same if we set plus equal to 1. So this means we need to increase every step this number. At the first, when it's true, when we have activation is 1, that will be 1. And we go inside and we got hide all and see only, where are you? New h, right? So by default this is 0, and we have some particles which will be true for this condition. So we have 6, and so 1, and every frame we will add it some numbers to this, so we have this grow effect. And this grow effect will be possible only if we check this under the flip solver, under the behavior, these h particles. Because if we don't do that, that will not be possible to do inside of even a subsolver. The next step, we have these bubbles. Now we have the group. From this grow, we have the group bubbles. Again, we create another point at wrangle and working on the bubbles. Group was specified here. And we could say for this bubble something like that. When we fit our new h is the attribute which is I have just shown you, from 0 to 15. So from moment the particles is go inside this group and 15 frames later. So we want to grow from this range to p scale, from our initial p scale that this particle has already, to the p scale plus some number. P scale plus, again, some random numbers, the same as we did before. This way we have this simulation for the particles, which the particle, I need to go here and I want to show it a little bit faster. So we have this simulation of this, for example, this guy is growing inside of our subsolver, and that is going not just simultaneously for every particle which is going inside this group, but the time it's going inside this group. So Houdini knows that this particle just have considered as a member of your group, and now you could grow it. Okay, let's go inside. Let's see what we have else. And one more thing, we need to specify that after 5 frames in this new h, we want to create another group and call it kill. So this will allow me to kill some particles after a few frames. And I'm talking about this big one. So not the smaller one, but the big one, and that will kill at something. And you have this movement, like the popping of the bubbles inside of your simulation. In order to do that properly, you need to create a pop wrangle, and I did it here. I'm working with the kill group, which is this last one. And again, random from ID, I use some seed to change the randomness. If it's bigger than some arbitrary number, remove a point based on your ID. So this is randomly kill some bubbles. The next thing is here. I just try to multiply it by -1 the velocity of our simulation when it goes too high. And pop kill is a like bounding box of our simulation, I guess, which I couldn't see, and this is kill any particle that go beyond this. So just simplify a bit, and that's it for for this part, I guess. Let me see. Okay, we could go outside. I use this wrangle just to visualize your points, because by default this points is something like that, right? And if you write GL sphere points equal to 1, that will represent not just only a sphere but also consider your p-scale that you have. So you could, it will not affect your render, but it will give you an idea of what that looks like. If you go with the material level, so you check this guy and go to the material. I create a bunch of materials, and I think that was used for our points, and I'm not sure why you show me that, because right, I did it this way. And of course you want to go to your Redshift particles, connect this. If you want some I'm not sure if I need to enable this guy, but for sure I need to go to the out ROP and be aware of instance particle blue. And inside of here we want Fresnel. We want, let me grab and check if we could show you something at least. Main particle, right. So this is our Fresnel by default, and I remap that with some color, right? I use it as a diffuse and as the reflection color for the material. Material is pretty standard. I didn't do nothing. It's glass, but I ended up just disable our refraction, just like a plastic material. And I used this guy and this guy with a different color, and I blend it based off our temperature. So in the material, I just again point, I think it's like particle attribute node for Redshift, and I use it material blender and as a mask for the second one. So this way, I need to disable this. When we have these bubbles, we have different materials for it, right? It's not, for example, that more colorful, for example. It has different properties a bit. It has backlighting transparency, right? It's more like lighting. And we have this wave, this another ramp, going for particle attribute, use a ramp and use it as a emission color right here. And this way we have this wave of particles, of ground particles, as you could see. And you could lit it up with just a little bit of emission weight. That's like an impact before we grow into the different particles. That's it for the material. Let's go for the ROP. And as always, we start with the basic, go to the advanced, go to the system. Probably you want to change this bucket size. If you have more than one video cards, you can do that, I guess, but I use on an older version of Redshift because I bought it back in the day when we're not using every month subscription, but just 1 year permanent payment, and I still use that. Then I guess what else? I used the automatic sampling. You could play around with that. Did it back in the day, but I'm not sure if I want to go back to this whole. I used the motion blur. I used the globals with a pretty standard, and of course hardware ray tracing if you have RTX video card that will speed up your render. Just the pretty standard settings for global illumination. In this case, I could go with even brute force, different method of global illumination, because I don't have a lot of, for example, diffuse materials or inside of some room when we have bit bounds of your global illumination, just transparency and reflection. That's it. And that's it for now, I think. What else? Nothing special here. Just specify your format, specify your camera, and be aware of render frame range, not just the frame, and press render to disk and you will have it. See you next time. I will involve in this Houdini stuff and try to bring you something new. Having a good day and bye bye.